Section 10.1 Correlation. Key concept. We introduced the linear correlation coefficient R, which is a number that measures how well paired sample data fit a straight line pattern when graphed. We use the sample of paired data, sometimes called bivariate data, to find the value of R. And then we use R to decide whether there is a linear correlation between the two variables. We consider only linear relationships, which means that when graphed in a scatter plot, the points approximate a straight line pattern. Then we discuss methods for conducting a formal hypothesis test that can be used to decide whether there is a linear correlation between all population values for the two variables. Finally, we discuss the method of randomization, whereby we resample many times to test the null hypothesis of no correlation. Okay, so the basics. Concepts of correlation. We begin with the basic definition of correlation, a term commonly used in the context of an association between two variables. Now, a correlation exists between two variables when the values of one variable are somehow associated with the values of the other variable. A linear correlation exists between two variables when there is a correlation and the plotted points of paired data result in a pattern that can be approximated by a straight line. Interpreting scatter plots. In part A, it says, a distinct straight line or linear pattern, we say that there is a positive linear correlation between x and y, since as the x value increases, the corresponding y values also increase. So this is a representation of a positive linear correlation. So here you can see all the data that's going increasing, and then we have positive correlation. We have R, which is equal to 0.859. Okay, and then we have a distinct straight line or linear pattern where we say that there is a negative linear correlation between x and y, since as the x values increase, the corresponding y values decrease. So therefore, here is a picture of a negative linear correlation. And you can see here that the negative correlation is R, which is equal to negative 0.971. Next, we have no distinct pattern, which suggests that there is no correlation between x and y. So this would be considered a no correlation graph. And no correlation has a value of R where it's close to 0, which is 0.074. And then a distinct pattern suggesting a correlation between x and y, but the pattern is not that of a straight line. So in this case here, this particular graph would represent a possible correlation between x and y, but it's not that of a straight line. And therefore, the non-linear relationship R is equal to 0.330. Okay, measure the strength of the linear correlation with R. Okay, so if we take a look at all these four scenarios, okay, for the graphs, because conclusions based on visual examination of some scatter plots are largely subjective, we need more objective measures. We use the linear correlation coefficient R, that is a number that measures the strength of the linear association between the two variables. So here for the positive correlation, we see that R is equal to 0.859. For the negative correlation, we have R, which is equal to negative 0.971. For no correlation, we have R, which is equal to 0.074. And for the non-linear relationship, we have R, which is equal to 0.330. Okay, now the linear correlation R measures the strength of the linear correlation between the paired quantitative x values and y values in the sample. The linear correlation coefficient R is computed by using formula 10.1 or formula 10.2 included in the following key elements box. Now the linear correlation coefficient is sometimes referred to as the Pearson product moment correlation coefficient in honor of Carl Pearson from 1857-1936, who originally developed it. Now, because the linear correlation coefficient R is calculated using sample data, it is a sample statistic used to measure the strength of the linear correlation between x and y. If we had every pair of x and y values from an entire population, the result of Formula 10.1 or Formula 10.2 would be a population parameter represented by the Greek letter rho. So, calculating and interpreting the linear correlation coefficient R. The objective is to determine whether there is a linear correlation between two variables. The notation for the linear correlation coefficient: n represents the number of pairs of sample data. The summation symbol denotes addition of the items indicated. The summation of x is the sum of all the x values. The summation of x squared indicates that each x value should be squared, and then those squares are added. And this is the sum of x squared indicates that the x value should be added, and then the total then squared, and avoid confusing these two different scenarios. And the sum of xy indicates that each x value should first be multiplied by its corresponding y value, and then after obtaining all such products, we find their sum. R represents the linear correlation coefficient for sample data. Rho is the linear correlation coefficient for a population of paired data. Now the requirements. Given any collection of sample paired quantitative data, the linear correlation coefficient R can always be computed, but the following requirements should be satisfied when using the sample paired data to make a conclusion about linear correlation in the corresponding population of paired data. Number 1, the sample of paired data XY data is a simple random sample of quantitative data. Number 2, visual examination of the scatter plot must confirm that the points approximate a straight line pattern. Number 3, because results can be strongly affected by the presence of outliers, any outliers must be removed if they are known to be errors. The effects of any other outliers should be considered by calculating R, and without the outliers included. Now, for the requirements of 2 and 3 or above are simplified attempts at checking this formal requirement. The pairs of XY data must have a bivariate normal distribution. Number 1, you state the claim and the opposite of the claim. Number 2, you identify the null and the alternative hypothesis. The null hypothesis is the statement is assumed true until evidence indicates otherwise. The alternative hypothesis is the claim to be tested. And the examples and exercises in this section generally involve two-tailed tests, but one-tailed tests can occur with the claim of a positive linear correlation or a claim of a negative linear correlation. In such cases, the hypotheses will be as shown here. So for the two-tailed, left-tailed, and right-tailed, we see that rho is going to equal 0 for the null hypothesis. For the alternative hypothesis for the two-tailed, rho does not equal 0 for the alternative hypothesis. For the left-tailed test, the alternative hypothesis is that rho is less than 0. And for the right-tailed test, the alternative hypothesis is that rho is greater than 0. Now recall that the alternative hypothesis is the one not containing equality. So the alternative hypothesis uses the symbol less than, greater than, or not equal to. And the null hypothesis is the symbolic expression that the parameter equals the fixed value being considered. Number 3, you're going to use the alternative hypothesis to determine whether it is a left, right, or two-tailed distribution. Number 4, you're going to select the significance level alpha. Now, based on the seriousness of a type 1 error, make alpha small if the consequences of rejecting a true null hypothesis are severe, and the values of 0.05 and 0.01 are very common. Number 5, formulas for calculating the linear correlation coefficient R. So formula 10.1, R is going to equal n, the sample size, times the sum of x times y, minus the sum of x times the sum of y, divided by the square root of n times the sum of x squared, minus the sum of x, and then square that, times the square root of n times the sum of y squared, minus the sum of y quantity squared. This is a good format for calculations. Now for 10.2, we have the following. R, which is equal to the sum of the z-score of x times z-score of y over n minus 1. And this is good format for understanding. Now, where zx is going to denote the z-score for an individual sample value x, and z subscript y is the z-score for the corresponding sample value y. And then rounding the linear correlation coefficient r. You round the linear correlation coefficient r to 3 decimal places so that its value can be directly compared to critical values. Number 6, the test statistic for linear correlation, with the null being that rho is equal to 0. T is going to equal r over the square root of 1 minus r squared divided by n minus 2, with the degrees of freedom is equal to n minus 2. And number 7, find the corresponding p-value or critical value. So on the left side, we're going to go ahead and see you can draw the curve and then label using the p-value method. The p-value methods are provided by technology or using the t-distribution table A3 with degrees of freedom df is equal to n minus 2. For the critical values, we're going to use table A6 to interpret r, and we're going to consider critical values from table A6 as being both positive and negative and draw a graph similar to the figure below. So let's take a look at table A6 in the back of the book on Appendix 6. So here you're going to see this is table A6 and it's titled Critical Values of the Pearson Correlation Coefficient R. So whatever your values of n is going to be, if alpha is equal to 0.05, you're going to choose that critical value. If alpha is equal to 0.01, then you're going to choose that critical value. So again, this represents the test when the null of rho is equal to 0, which is no correlation, against the null hypothesis where it's not equal to 0, which is correlation. So we'll discuss more about that. So let's go back to the critical value method. So with the critical value method, once we have our critical values, we write our critical values, and then we take the value of r that we got within the in step 6. Okay? And that, or the value of r, excuse me, not in step 6. Step 6 would be used for the p-value. Okay, for the value of r, we would take the value of r that we find here in step number 5. And then we would find out whether this value is going to be in the correlation region or in the no correlation region. So the correlation region, no correlation, is going to be in between the critical values of r. And the correlation is going to be the regions outside of those critical values. So when we make a decision for the p-value, we reject the null if the p-value is less than or equal to the significance level, which supports the claim of a linear correlation. And we fail to reject the null if the p-value is greater than the significance level, which does not support the claim of a linear correlation. Now for the critical value method, we reject the null, there's a correlation, if the computed linear correlation coefficient r lies in the left or the right-tailed correlation region beyond the critical value for that tail. You conclude that there is sufficient evidence to support the claim of the linear correlation. And then you fail to reject the null, which is the no correlation, if the computed linear correlation coefficient lies between no correlation region, the two critical values. You conclude that there is not sufficient evidence to support the claim of the linear correlation. So here is your conclusions. If you have a correlation, you would say that there is sufficient evidence to support the claim of a linear correlation that followed by the original claim. And then you have no correlation, you would state that there is not sufficient evidence to support the claim of a linear correlation that followed by the original claim. Now, properties of the linear correlation coefficient r. Number 1, the value of r is always between -1 and 1 inclusive. That is, r is either greater than or equal to -1 or less than or equal to 1. Number 2, if all values of either variable are converted to a different scale, the value of r does not change. Number 3, the value of r is not affected by the choice of x or y. Interchanging all x values and y values, and the value of r will not change. Number 4, R measures the strength of a linear relationship. It is not designed to measure the strength of a relationship that is not linear. Number 5. R is very sensitive to outliers in the sense that a single outlier could dramatically affect its value.